Okay, good afternoon. So, in the last class, we started cyclic codes. So, this class, we will do a couple of more things in the cyclic code. So, I'll just recall a few things from the last class. A code is called cyclic code if two conditions are satisfied. First, C is a linear code. That means it's a k-dimensional subspace of some vector space of some fixed length n. Second, any cyclic shift of a code word is also a code word. That means if C0, C1, C2, Cn minus 1 is a code word in C, its cyclic shift is also in C. Okay. And I think we have seen a couple of examples last time that this is a cyclic code. Second example is not a cyclic code. Okay. But if we interchange third and fourth column in all the code words, we get a cyclic code. Okay. And so on. Now, now it's very important to observe that one very interesting feature that once we do this mapping, like when we do a mapping of a code word into a polynomial, like C0, C1, C2, Cn minus 1 is a code word, and we map to a polynomial C0 plus C1x plus C2x square plus dot 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 Cn minus 1 x square minus 1, I call it Cx, then what is the meaning of cyclic shift in the polynomial? So means x times Cx will be nothing but C0 times x plus C1 times x square plus dot 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 last coefficient Cn minus 1 times x raised to power n. Now this will be in core, will again be in C provided, because you see that there is no degree n here, so this should be 1, then only it is possible. So that means x times Cx is a code word if and only if x is power n is equal to 1, and this gives a condition that when we do this mapping of code words or vectors into this, we get a polynomial ring. And very nice example is this. If you look at the space Z2 raised to power 3, this is a vector space of length 3. All 8 code words are there, or all 8 vectors are there, and the corresponding polynomials I can write. Okay. So this is nothing but Z2x modulo xu minus 1, because length is 3 here, n is equal to 3. So we take all the polynomials and we reduce it to modulo xu minus 1. So this is a polynomial ring. We denote it by R3. Okay, this is not a field. So we can add, subtract, multiply, and but cannot divide. Okay. So an ideal in this ring. What is the ideal? Let me give you a definition of ideal. I think you will recall what is ideal. If R is a ring, I is a subset of R. A subset of R is called as an ideal if A plus B and A minus B belongs to I for every A and B in I, and left multiplication by the ring element R is the element in the ring R times A gives you I, an element in I. Okay. If it is close to the multiplication, scalar multiplication from left from the ring, then we call I as an ideal. So very nice example was I is equal to 0, 1 plus x square, x plus x cube is an ideal in f2x slash x cube minus 1 ring. Now this is clear. If you take this 1 plus x square and x plus x square, these 4 elements forms an ideal. Okay, they satisfy all the properties of an ideal. Now there are a couple of other examples of ideal. Okay.
Sir?
Yes.
Sir, your voice just distorted.
Now is it coming?
Yes, sir.
Okay. Sorry. So, when a couple of other examples which I can mention to you. For example, if you take ring as fqx modulo x raised to power n minus 1. Okay, and if x is a polynomial which is a factor of x raised to power n minus 1, then all polynomials divisible by gx an example of. Okay, you can try all the properties. Okay, is known as principal ideal or principal ideal. What do you mean? Okay, so suppose R is a ring. Okay, and I is an ideal. Okay, say that I is a principal ideal. I is nothing but pi if an element G in I such that I is generated by G. What do you mean by this? This is nothing with G times R, that R belongs to R. Okay, all okay. So if this happens, then G is known as generator of R. That I is generated by G. Okay. Ring is principal ideal ring if every ideal of R is principal. Okay. So okay. So let example R3 R3 is equal to F2x modulo x minus 1, our previous example. Okay, and if we take ideal I to be 1 plus x plus x square and 1 plus x square, this is ideal in this ring. So then we say that this ideal is generated by plus x. So that means it is a principal ideal. Now how do I check this? If I take 0 times 1 plus x, we are going to get 1 plus x 0, which is the same thing as 1 plus x cube, right? Which is a 0. Okay, this is also same thing as 1 plus x square times 1 plus x. Same thing, right? X cube, remember x cube plus 1 is same thing as x cube minus 1. Everything is modulo 2, okay? Then we have 1 into 1 plus x is same thing as 1 plus x. This can also be written as x plus x square times 1 plus x. Okay, we have x times 1 plus x is same thing as x plus x square, which is same thing as 1 plus x square times 1 plus x. Okay, finally I can write down x square times 1 plus x is same thing as 1 plus x square is same thing as 1 plus x into 1 plus x. So I have taken all the elements and I can multiply and I can see that we are getting the elements in the ring. in the ideal I. Okay, so these are all principal I. So this ring is nothing but principal ideal ring. So basically, there is a result which I want to mention here. Theorem that the rings set of all integers fqx, the polynomial ring, and fqx modulo x to the power n minus 1 are all principal ideal ring. Okay, so these are all principal ideal ring. Okay, so you saw that there is a one-to-one correspondence. So basically, there is a one-to-one correspondence between this principal ideal I and the cyclic code, because these are nothing but, if you look at from the previous example, I mean the same example that we have taken, 0 can be written as 0 0, then we can write down 1 1. Okay, so 0 can be written as 0 0 0, and the 1 plus x can be written as 1 1 0. Then x plus x square can be written as 0 1 1, and last one can be written as 1 0 1. Okay, so I can write down these as the code words here. 0 0 0. This can be written as 1 1 0. This can be written as 0 1 1, and this can be written as 1 0 1. So this code is nothing but a cyclic code, right? So cyclic code corresponds to ideal in this principal ideal ring. This is a very important observation. So I can write it down as a properly as a theorem. A code C in Rn. What is Rn? Rn is nothing but fqx modulo x raised to the power n minus 1. A code C in Rn is cyclic code if and only if C satisfies the following properties. Number one, if ax and bx are two polynomials in C, this implies that ax plus bx belongs to C. Right. Second property, if ax is in C and say rx is in Rn, ring R, then rx ax belongs to C. So that means it is closed with respect to multiplication of any element of Rn. Okay, this is an element of Rn, arbitrary element of Rn. Okay, so this is a cyclic code. Now I am going to give you some basic properties of the cyclic codes. What are the basic properties of cyclic code? The first one, I am describing it as a theorem. C, of course I am taking a non-trivial one here, is a cyclic code in Rn. Suppose C is a cyclic code in Rn, then first property, there exists a unique monic polynomial gx of smallest degree in C. There exists a unique monic polynomial gx of smallest degree in C. Second, C is generated by gx. Okay. Third, means if any code word in C is a multiple of gx, right? Third, gx is a factor of x raised to power n minus 1. These are three very, very important properties of a cyclic code. If C is a cyclic code in Rn is a polynomial ring, fqx modulo x raised to power n minus 1, right? As I have shown to you is example of z2 raised to power 3. So basically z2x modulo x cube minus 1. Okay. Or I have shown you an example of R3. So I need to prove these facts. These are very, very simple facts to prove. Let me prove them one by one. First one. Suppose it is not unique. Suppose the polynomial gx is not unique. There are two polynomials gx and hx. Two polynomials gx and hx, both monic in C and they are of the smallest degree. Okay. Then what will happen? So then if there are two monic polynomials, then if I can consider gx minus hx. This is a polynomial of degree less than both gx and hx, right? And this has the smallest degree, which is a contradiction. So this polynomial is unique. This polynomial is unique, okay? Unique polynomial. Gx is a unique monic polynomial of smallest degree in C. Second, I have to show that this is first thing. Second thing, I have to prove that C is generated by C is basically generated by Gx. So how do we show that? So I'll take an arbitrary element Ax in C. Okay. Now, such that suppose it is not a multiple of Gx, but rather when we divide, there is some remainder. Ax can be written as some quotient polynomial Qx times Gx plus Rx, a remainder polynomial Rx, right? Where degree of Rx will be less than degree of Gx. I have just applied the Euclidean algorithm division. Okay. Suppose Ax is an arbitrary polynomial in C, such that Ax is nothing but quotient polynomial times Gx plus Rx, a remainder polynomial Rx. And of course, degree of Rx is less than degree of Gx. Okay. This implies that we can write down Rx polynomial as Ax minus Qx times Gx. I can write it down. I can take this other side, right? And this belongs to C. Okay. Now, degree of Rx, this shows that there is a polynomial. Now, degree of Rx is less than degree of Gx, right? But Gx is of the smallest degree. This shows that Rx is of the smallest degree, right? This contradicts the fact that Gx is of a smallest degree. Because we are getting another polynomial Rx degree less than Gx. Hence, this our assumption is not correct. And in other words, Rx is nothing but 0. So basically, this implies that Rx is nothing but 0 polynomial. It is not possible. This implies that Ax is nothing but Qx times Gx. Okay. So Ax belongs to multiple of Gx. This is the second proof. Okay. So C is a multiple of Gx, right? Which is our C. Okay. So this is our C. Third property says that Gx is a factor of x raised to power minus 1. Very beautiful property and very powerful property actually. So basically we will show that Gx is a factor of x raised to power n minus 1. Third property, we have to show that gx is a factor of x raised to power n minus 1. Okay, and the proof is really a simple one. By division algorithm, I can assume that x raised to power n minus 1 can be written as some quotient polynomial qx times gx plus rx, where degree of rx, remainder polynomial, is less than the degree of gx. Okay, this implies that by simple calculation I can show that rx is equal to minus times qx times gx, and if I reduce it to modulo x raised to power n minus 1, right, this implies that rx belongs to multiple of gx. Okay, again, since degree of rx is less than degree of gx and rx belongs to c, right, this means that by minimality of degree of gx, we must have rx should be 0. So once rx is 0, this implies gx must divide x raised to power n minus 1. So gx is nothing but a factor of x raised to power n minus 1. So gx is known as generator polynomial of cycle. Okay, gx is known as generator polynomial of cyclic code C. Fourth property I would like to mention now. Actually, from you can find out the generator of the code. Okay, if gx is of the form z0 plus z1x dot 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 gr, suppose there are coefficients, n minus 1, I can find a cyclic code.
Sir, screen is not visible.
I need to stop.
Yeah. Okay. It's visible now.
Okay. Okay, so now in that means if I want to find cyclic code of a certain length, what I should do, I should look at, suppose I want to find all cyclic code of length 3. So all I need to do is look at the polynomial x cube minus 1 and look at its factor. We know that I can factor it as x plus 1 into x plus x plus 1. Okay. So now I can find out all the binary cyclic codes. In fact, I can make a table for you. So we know that x cube minus 1 can be written as x plus 1, x square plus x plus 1. Okay. And I can list all binary cyclic codes. All binary cyclic codes. Codes of length 3. can do that. Just look at the factors of x cube minus 1. So when we take generator polynomial as 1 code in R3, all of R3, and code in F23, all of F23, whole space, trivial code. When we take generator polynomial as x plus 1, we get code in R3 as 0, 1 plus x plus x square. We saw this example earlier, and 1 plus x square. And in terms of binary, we get 0, 0, 0, 1, 1, 0, 0, 1, 1, and 1, 0, 1. Right? When the code is x cube minus 3. When the polynomial is x square plus x plus 1, the other one. Okay? So the code in R3 will be 0, 1 plus x square, and the binary code is 0, 0, 0, 1, 1, 1. Okay? And when the polynomial is x cube minus 1, which is 0 here, so we get all 0, and here we get 0, 0, 0. So this is our table of all cyclic codes of length 3. And how we can get it? Because we can factorize. As you can see that 1 is a factor of x cube minus 1, right? X cube minus 1 is also a factor of it, right? Then these are two trivial factors. Then we have x plus 1 as a factor, and x square plus x plus 1 is a factor. So there are total 4. 2 factors of x cube minus 1. There are possible factors of x cube minus 1 are 4, right? 1, x plus 1, x square plus x plus 1, and the product of them, right, which is x cube minus 1 whole. So we get 4 cyclic codes. So we know in terms of vector space how they look like, in terms of the polynomial ring R3 how they look like, and in terms of the generator polynomial how they look like, right? So basically, let me list. So suppose C is a cyclic code, cyclic NKD code with generator polynomial dx, and we know that dx divides x raised to power n minus 1. So what happens that x raised to power n minus 1 can be written as gx into some other polynomial hx, right? Because the product of 2 will give you x raised to power n minus 1 for some polynomial hx. So this hx is known as check polynomial. Since gx is monic, hx is also a monic polynomial. Okay, so if degree of gx is n minus k, then degree of hx is k. Why we need degree of hx gx as n minus k? It will be clear in a minute to you. Why is that? Now, in fact, keeping this in mind, I can actually now give you an idea. I can give you a table of cyclic codes, basically, how we can find out. In fact, that means I should look at the factorization of x raised to power n minus 1. So let us look at n and factors of x raised to power n minus 1. And then I can say number of cyclic codes, how many will be there. Okay, so we have n is equal to 1. Polynomial is x raised to power n. I know x plus 1, which is x minus 1, same thing as x plus 1. And number of cyclic codes are 2. Okay, one generated by 1, another one will be x plus 1. If n is equal to 2, factors are x plus 1 whole square. Okay. Number of cyclic codes are 3. If n is equal to 3, factors are 1 plus x into 1 plus x square. We just saw this example. Okay. So number of cyclic codes are 4. For n is equal to 4, factors are 1 plus x raised to power 4. Number of cyclic codes are 5. You take product at a time, right? When n is equal to 5, products are 1 plus x, 1 plus x square plus x cube plus x raised to power 4. Okay. And number of cyclic codes are 4. When n is equal to 6, factors are 1 plus x whole square and 1 plus x square whole square. And number of cyclic codes are 9. Okay. When n is 7, factors are, this is the important one because this includes the Hamming code. 1 plus x square plus x cube and 1 plus x cube. Number of cyclic codes are 8. In case of n is equal to 8, we have 1 plus x raised to power 8 and number of cyclic codes are 9. Okay, when we have 9, factors are 1 plus x plus x square, 1 plus x cube plus x raised to power 6, and number of cyclic codes are 8. In case of n is equal to 10, it is 1 plus x whole square, 1 plus x square plus x cube plus x raised to power 4 whole square. Number of cyclic codes are 9. Okay, so this is ultimately a way of factorizing everything. So we will learn later in the course how to actually factor these things. How do we get these factors? For example, x raised to power 7 minus 1 is 1 plus x into 1 plus x square plus x cube into 1 plus x cube. How do we get these factors? I will show you with an example later on in the class how to get these factors. But these are the basic things. So basically, once we know these basic things, we know the cyclic code. Let us take the example of x cube minus 1, and I will show you. In fact, I'll give you one result here actually. Number of cyclic codes I can write down. So question A. PIs are distinct monic polynomials. PIX distinct monic possible polynomial. And suppose EIs are okay 1 less than equal to I less than equal to R. Then to R EI plus 1 cyclic codes of length n are possible. This is the most general result. If we can factorize x raised to power n minus 1 like x raised to power n minus 1 as this, then number of cyclic codes are this much. Okay, this is the most general result. Now let us focus on x cube minus x raised to power 7 minus 1, and I'll show you what are the codes. Okay, let us take an example here. So x raised to power 7 minus 1 can be factored as 1 plus x, 1 plus x square plus x cube, and 1 plus x cube. I will show you how to factor this, but this is the factor right now. You can actually multiply and see this is the factor. You can multiply this factor, you will get the answer x plus 7 marks. So this will give us two binary 7-3 cyclic codes. So how do we see this? One will be generated by 1 plus x into 1 plus x square plus x cube, and that will be 1 2 3 4 5 6 7 1 1 1 0 1 0 0 0 1 1 1 0 1 0 0 0 1 1 1 0 1 1 0 0 1 1 1 0 0 1 0 0 1 1 1 comma 1 0 1 0 0 1 1 1 1 0 1 0 0 1. Okay, this is the first one. Second one, 1 plus x multiplied by 1 plus x cube will give us a code 7 zeros 1 0 1 1 1 0 0 0 1 0 1 1 1 0, then 0 0 1 0 1 1 1 1 0 0 1 0 1 1 1 1 0 0 1 0 1 1 1 1 0 0 1 0 and 0 1 1 1 0 0 1. These are the two 7-3 binary cyclic codes generated by this. Okay. Now, I will show you how the cyclic codes are encoded actually, and there is a very basic result here. So first, let me mention the theorem for you. So theorem says that let gx be the generator polynomial of an ideal of Rn is equal to fqx modulo x raised power n minus 1. Then the corresponding cyclic code has dimension k. Okay, if the degree of gx is n minus k, and in that case, so c is generated by gx. If gx is degree n minus k, then the dimension of c is k. So how this encoding is done, let me show you. We have cx is equal to message polynomial mx into generator polynomial gx. So message polynomial is m0 plus m1x plus mk minus 1 x raised for k minus 1 into z0 plus z1x gn minus k x raised for n minus k is equal to c0 plus c1x n minus 1, x raised to n minus 1. This degree cannot exceed n minus 1, this degree cannot exceed k minus 1, and this degree cannot exceed n minus k. So the sum will be n minus 1, right? So this is perfectly matching. So how do we encode? From this cyclic code, take the message bits, convert them into a message polynomial m0. Message bits are m0, m1, m2, dot 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 mk minus 1, and the corresponding message polynomial will be m0 plus m1x plus m2 x square plus dot 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 mk minus 1 x raised to k minus 1. Multiply it with the gx, which is of degree n minus k. So the result will be n minus 1. And this is how you get the, uh, the corresponding degrees are okay. This fact this term, okay. And degree of cx, suppose less than equal to k minus 1. So for two polynomials c1x and c2x, suppose there are two distinct polynomials c1x and c2x, such that degree of c1x is less than equal to k minus 1 and degree of c2x is less than equal to k minus 1, then we know that gx times c1x will not be equal to gx times c2x, right? So basically, how many choices are there for such polynomials? So it is clear that we can say that quality of s will be q raised to power k. Okay. And c2x are distinct. Will also be distinct from gx c2x. They're all distinct actually. So the thing is that the cardinality of s will be q raised to power k. Now s is subset of code generated by gx. Okay. Now on the other hand, if you take for any code word x with ax in the polynomial fqx, what we can write axg ax as some polynomial ux x raised to n minus 1 plus vx, where degree of vx less than n. Gx minus ux times x raised to n minus 1. This implies that modulo x raised to n minus 1 dx divides x. Okay, so write Vx, you can write Vx as Gx times Bx for some polynomial Bx, for some Bx with degree of Bx less than k. Since the code has S, this implies that set generated by G is a subset of S. So and so degree of Gx is n minus k, and generator matrix of G can be written as Gx x times Gx dot 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 x raised to k minus 1 times Gx. Okay, so that means it is nothing but the cyclic shift of Gx. Okay, let us take an example and so it will be clear to you. If we have 7 4 2 cyclic code, C generated by 1 plus x square plus x cube, G can be written as Gx x squared x to 0 0 1. Okay. Okay, there are two more results I would like to mention. For if C1 and C2 are cyclic codes, C1 and C2 are cyclic codes, it's G1x and G2x, then C1 C2 if and only if. So I leave it as an exercise for you to prove that G2x divides G1x. Okay. Another theorem, the dual of a cyclic code is also cyclic.